The idea that an active nanosystem could behave like Maxwell's demon feels audacious. A ghost from a Victorian thought experiment reaching into a modern microfluidic chip. A nanomotor swims in a noisy bath, kicked by thermal fluctuations while it burns chemical fuel. To the naked eye, its path is jitter. But what if we watch that path in real time, and with exquisitely timed magnetic or electrothermal nudges, tip the odds ever so slightly, letting favorable fluctuations add up while damping the rest? If we succeed, the motor's random motion would be rectified into useful work without breaking the second law, because the missing cost reappears in the bookkeeping of information. Isn't it haunting that the demon's finger, once purely imaginary, might be replaced by a feedback loop running at kilohertz on a microscope stage? From a scientific perspective, the bridge is information thermodynamics. At the nanoscale, every step of a chemically powered motor comes with a ledger. Work done on loads, heat dissipated to the fluid, entropy produced along the trajectory, add measurement and feedback, and another term enters. The information gained about the system's state. The generalized second law says that the extractable work is bounded by the information you acquire, and pay to process and erase. In plain terms, you cannot cheat thermodynamics, but you can trade bits for joules. Doesn't this suggest that a demon is not a violator of physics, but an accountant? Converting knowledge into work at a fair price. Engineers see an experimental path. Track single Janus motors at high frame rate, infer their instantaneous velocity and heading, apply micro nudges, short magnetic torques, local optothermal kicks, weak AC fields. Only when the motor's fluctuation aligns with a chosen direction. Do nothing otherwise. Over many cycles, those conditional pushes turn an unbiased random walk into a steady drift against a load or up a shallow gradient. Meanwhile, we log the mutual information between the measurement stream and the motor's state, the energy consumed by actuators, and the chemical fuel spent by the motor. If done right, the inequality, work less than equals kBTx information plus actuator input, closes within error bars, and the demon earns its keep without magic. The methodology shifts the lab from watching particles to running a real-time codec. The environment writes a noisy signal into the motor's trajectory. Our cameras and estimators decode state in milliseconds. The controller encodes a tiny bias back into the motor's dynamics. The same videos that once proved a particle was alive now yield work distributions, entropy budgets, and energy per bit numbers. Change the narrative from fighting noise to harvesting it, and the demon emerges not as a myth, but as a control policy. What would count as a first? 2 clean demonstrations. 1, a feedback rectified nanomotor that lifts a calibrated colloidal load, or pumps tracer particles, with net positive useful work. And 2, a field mapper, where feedback turns tiny, otherwise undetectable gradients into a statistically reliable signal, quantified as bits per joule. Success looks like this. Open loop, the motor meanders. Closed loop, it acquires a finite drift and delivers work. Across conditions, the extracted work scales with information rate, and the full energy information ledger balances with an uncertainty. Wouldn't that be the first true Maxwell engine built from autonomous chemical motors rather than externally trapped beads? Force, demons are slippery. Latency kills. If measurements and nudges lag the dynamics, you push the motor after the moment has passed. Back action matters. Actuators add heat inflows that must be counted. Hidden fuel channels can masquerade as information gains. The cure is rigor. Flowless microchambers to suppress hydrodynamic bias, GPU pipelines to cut control delay, passive colloids and dead motors as controls, shuffled label tests to ensure estimated information isn't an artifact. Thermodynamic uncertainty relations provide lower bounds on entropy production when full energetics are hard to measure, keeping the demon honest. If such a system works, the implications spill beyond a single experiment. We would have shown that active matter, already spending energy internally, can be steered by information into doing extra useful work on demand, with an audit trail that satisfies the generalized second law, that bridges the gap from Maxwell and Szilard to deployable microtechnologies, self-poised nanosensors that amplify weak signals with minimal energy overhead, micropumps that harvest fluctuations to move reagents on a chip, diagnostic elements that convert a few bits of real-time knowledge into deterministic action. The paradox, then, is that an active daemon is both humble and profound. Humble because its miracles are just smart timing plus tiny nudges. Profound because it turns randomness into a resource and elevates information to the same footing as fuel. Out of jitter comes work. Out of measurement comes control. Out of a century-old thought experiment comes a blueprint for nanoscale machines that do not fight noise, they live from it. The question that remains is not whether a nanomotor can move, that has long been settled, but how close such a daemon can come to the ultimate bargain of nature. One bit of certainty for the smallest possible price, paid and tallied in full. Maxwell's daemon, a 19th century idea, imagines a tiny being that observes gas molecules and selectively opens a door to let fast ones through. By doing so, the daemon decreases entropy and extracts useful work from thermal noise. For over a century, this paradox challenged the second law of thermodynamics. Modern information theory resolved it. The daemon must pay an energetic cost to acquire and erase information, restoring the law. Yet the idea remains a guidepost for how measurement and feedback can turn randomness into utility. The challenge now is not to imagine a daemon, but to build one. Tawabi et al., 2010, demonstrated an information engine by using feedback to bias colloidal particles, effectively implementing a daemon. It is like a bouncer at a club who admits only energetic dancers, slowly filling the dance floor with motion. Unlike passive colloids, catalytic nanomotors already consume fuel and move persistently in noisy environments. Their trajectories encode information about gradients, collisions, and random fluctuations. This makes them natural candidates for daemons that harvest fluctuations if guided by feedback. Rather than being externally driven probes, they are autonomous agents with internal energy budgets. The daemon role is not imposed from outside, but emerges from how their motion is read and nudged. This creates the possibility of daemons embedded in active matter itself. A Janus motor in hydrogen peroxide zigzags randomly but tends to climb gradients. With feedback, its noise can be rectified. It is like a scout dog running erratically but nudged by a whistle at the right time to always head toward the target. The daemon requires two steps: measure the system and act on the measurement. At nanoscale, high-speed cameras, real-time tracking, and microelectrodes can provide the measurement channel, feedback, pulses, magnetic, electric, or thermal nudges, then bias trajectories. If these interventions are timed to fluctuations, motors climb gradients or lift loads more efficiently than by chance. This transforms passive observation into active control. The cost of acquiring and processing information must be carefully included to remain consistent with thermodynamics. GPU-controlled feedback can rotate a motor whenever its orientation aligns with a favorable direction, rectifying random runs. It is like steering a kayak by dipping the paddle only when the current aligns with your goal. Information thermodynamics shows that work extracted from fluctuations must equal or fall below the information gained times the Landauer cost per bit. Active systems complicate this by already consuming fuel, so energy budgets must separate propulsion, dissipation, and feedback contributions. The paradox is whether the added information channel can turn unavoidable noise into extra usable work without breaking the second law. Experiments would test equality conditions of fluctuation. Theorems under activity. Success means showing bits per joule harvested in line with theory. Measuring peroxide consumption alongside trajectory bias quantifies energy per bit performance of a motor daemon. It is like running a factory where every scrap of waste is recycled into useful output. But the bookkeeping must prove nothing was stolen. What was once a philosophical debate becomes an engineering problem with microfluidic chips. Channels with built-in gradients and electrodes provide arenas where motors can be tracked and guided. Feedback software acts as the demon's brain, deciding when to intervene. Instead of a mythical being, the demon becomes a loop of optics, computation, and actuation. This shift brings Maxwell's paradox into the lab. With testable metrics, TMS, skill, active matter becomes the playground for thermodynamic demons. A microchip where motors climb chemical gradients more efficiently under feedback than without it shows the principle in action. It is like converting a campfire story into a working prototype in your garage. The first demonstration of demons built from autonomous nanomotors would be a milestone. It extends stochastic thermodynamics from externally trapped particles to self-propelled active matter. It probes whether feedback control works differently when the probe itself is alive with propulsion. It asks if intrinsic activity and extrinsic information combine additively or in new ways. Results could redefine the boundaries between passive and active systems. They would also test deep principles of the second law in noisy-driven contexts. Comparing entropy production with and without feedback reveals whether information engines improve efficiency. It is like finding out whether a marathon runner with a coach in their ear performs differently from one running blindly. If successful, active demons could form the basis for ultra-low power sensors and actuators. Instead of batteries, they would draw fuel from the environment and harvest information from noise. Chips with motor demons could map toxins, detect gradients, or transport cargo with minimal external input. Their efficiency would be benchmarked not in speed, but in bits per joule. This opens a new computing paradigm embedded directly in fluids and biological media. Motor arrays could detect pollutant gradients in rivers by rectifying noise into information maps. It is like a flock of birds navigating by turbulence itself rather than GPS. Critics will ask whether this is truly new or just a rebranding of biased motion. Distinguishing genuine information thermodynamic harvesting from trivial fuel-driven drift requires strict controls. Dead motors, shuffled labels, and reversed gradients must yield no information advantage. Latency and feedback loops could erase theoretical gains. The burden is to show real rectification of noise into work consistent with information inequality. Without this rigor, the demon risks becoming a metaphor again. Control experiments with passive beads ensure that observed effects are not just hidden flows. It is like testing a magician's trick under bright lights to see if it's real skill or sleight of hand. The paradox is that nanomotors, noisy and purposeless alone, may become demons when watched and guided. Randomness itself becomes a currency, rectified into directed work and coded signals. Yet the rules of thermodynamics remain unbroken. The cost of knowing and acting is always paid. Still, the ability to build demons out of matter challenges the once clear line between thought experiment and device. The nanoscale blurs philosophy with engineering. Maxwell's paradox becomes a laboratory reality. A feedback-guided nanomotor lifts a microscopic bead using only fluctuations and minimal fuel. It is like proving that whispers can be harnessed to push a wheel.